All right, more right-hand rules. And you can see this whole unit is nothing but right-hand rules, like one right-hand rule after another, and there are going to be more coming up in the next chapters. And so we're looking at here a torque on a current loop, and so you can see that in this loop, where the magnetic field is into the page, and you've got this rectangle where the current's going around, the force on all the sides are just, pulling outward on this thing, and so the net force is 0, and the net torque is 0. Okay, and so then, but what if we change it a little bit and we have this loop now, and it can turn, right? And so if we turn this thing, imagine that I've got, a magnetic field going, so something like this, and I have a magnetic field going this way, up from the ground. So that actually might be more like what's on next page. It's not quite yet. Okay, so magnetic field going up. So IL cross B, so there's nothing here, no force on this, no force on this. So here's IL cross B. That's going to create a force this way, right, on the top part, and here on the bottom you've got I going that way. So IL cross B, that's going to create a force going this way, right? And so then that's going to make this thing turn. And so since it's causing rotation, this thing has a moment, what I might call a moment of inertia, and that is NIA cross B. Right? The area vector crossed with the, because here, if I'm holding it this way, the area vector would actually be pointing towards me. And so A cross B, the area vector and the magnetic field have an angle of 90 degrees. Right? Here, it turns out to be 0. Right? And so the torque is IA cross B. It gives you the torque. And if you've got a number of loops, then you just multiply by the number of loops that you have. Right? And so now we have a dipole moment. And the moment is given by that mu. See that mu there? So tau equals mu cross B. So IA is what gives you mu. And NIA, if you've got multiple loops, the number of loops times the current times the area vector gives you the dipole moment, which is also a vector. Okay, and then there's comparing that potential energy. There's a, comparing electric, the dipole moment to a magnetic loop, right? Instead of having a magnetic dipole, well, we've kind of created a magnetic dipole using a current loop, right? And then, just comparing what that looks like for those.